So our next speaker is Anusha Krishnan. So now she is working at Syracuse University, and today she'll speak about prescribing Ricci curvature on a product of spheres. Thank you, Anusha, for accepting this invitation.
Okay, thank you, Romina, for the introduction, and thanks to all the organizers for organizing this session and for the invitation to speak here. So I will be talking about some joint work with TImothy Buttsworth from University of Queensland. So let me get started. So here is the prescribed Ricci curvature problem. So given a symmetric 2 tensor T on some manifold M, does there exist a metric G that realizes T as its Ricci tensor? Okay, so this is the prescribed Ricci curvature problem. I abbreviate it here as PRC. I might refer to that later. Since the Ricci tensor is a second order differential operator in harmonic coordinates like the Laplace of the metric or a multiple of the Laplace of the metric. So heuristically, this is like a Poisson equation for the metric. It's a second order differential equation. However, it's not as simple as the as just a Poisson equation because the Ricci operator is both highly nonlinear as well as not elliptic, which makes things very challenging from the point of view of an existence question. Another thing I want to point out before going on is that we're looking at the Ricci tensor, which is scaling invariant. And so uniqueness for this question is only up to scaling at best. So if G is a solution to this equation, then lambda times G for some positive number lambda is also a metric that solves this equation. Yeah, so I'll be talking about some history of this quite classical problem, followed by some recent work in the presence of symmetry. But first, just to contrast with the question of prescribing Gauss curvature or prescribing scalar curvature, these problems are very well understood, in fact, by work of Kasdan and Warner in the 70s. So here, of course, you're prescribing a scalar function, which is, while challenging, still perhaps easier than prescribing a Ricci tensor. One more thing I want to just mention is one very famous situation where the prescribed Ricci curvature problem has a complete solution is the situation on Kähler manifolds. So here, this is the subject of the Calabi conjecture. So again, proved by Yau in the 70s. Okay, but except in this Kähler situation, where the problem is very well understood, in general, this is a very challenging and open area. So this is a partial differential equation. Could start by talking about local existence. And this was addressed by Denis de Turck in the 80s, where he proved that if T is a tensor that is non-degenerate at some point, then you have existence to this prescribed Ricci curvature equation in a neighborhood of that point. Okay, and so this is essentially like an inverse function theorem type of result. However, complicated by the fact that the Ricci tensor, the Ricci operator is non-elliptic. And so his approach, similar to his idea for the short-term existence of the Ricci flow, known as the de Turck's trick, is to add in an extra component corresponding to the second Bianchi identity, which converts this non-elliptic operator into something which is elliptic, and you can proceed from there about the existence. So in general, the second Bianchi identity is something additional that needs to be satisfied. So the prescribed Ricci curvature equation is intrinsically overdetermined. However, he manages to show that this modified PDE, in fact, its solution is in fact, again, a solution to the um, original prescribed Ricci equation. So this addresses local existence. Non-degeneracy of T at a point is enough. So surely there are Ricci tensors of some metrics that are, say, you have Ricci flat metrics. So perhaps non-degeneracy everywhere is not really necessary, but it would at least guarantee you local existence. So, and one very easy way to ensure that T is non-degenerate at every point is to ask that T is itself positive definite, so it is itself a Riemannian metric. And this seems to be the assumption in all the past works that I've seen. So one that I'd like to mention is this work of Hamilton from the 80s, which says that if T is itself a metric on the two sphere, then you have existence for this equation if and only if so of T. Okay, so recall again, we are looking at the Riemann tensor, which is scaling invariant. So what this result says is that any metric T on S2 if it scale it so that it has volume pi, is of due to Dieter, Coiso, and independently Hamilton, says that if T is a metric on a closed manifold, then it's possible to scale T beyond a certain level so that it is not the of the metric. So you involves the prescribed some partial differential inequality satisfied by the scalar curvature on with positive definite changes. Okay. And so this result and the preceding one, they suggest that the correct question then, when you're looking at prescribing Ricci on a compact manifold, is to look both for the metric G and the scaling constant C, so that Ricci G equals this scaled version of T. Okay, so I'm calling this the prescribed Ricci curvature equation with scaling, and that's what we're going to look at in the rest of the talk. And there were results, existence results near Einstein matrix using perturbation techniques for this prescribed Ricci curvature with scaling. So something due to Dieter in the 80s, and then some results in the early 2000s. Right. So maybe those lend some heft to the fact that this is the right equation to study. However, after these results, the only other results known in general are in the presence of symmetry. Okay, so we'll now be looking at this prescribed Ricci with scaling in the presence of symmetry. Recent years, there has lot in this equation in the homogeneous setting by a number of authors studying existence questions on homogeneous spaces and Lie groups, looking at Ricci iteration, looking at the Ricci invertibility on the space of invariant metrics on homogeneous spaces. So in recent times, there's been a lot of work in the homogeneous setting. However, in the compact cohomogeneity 1 setting, until recently, the only existence result known was the following work of Hamilton, which says that if T is an invariant rotationally symmetric metric on the 3-sphere, so that its own Ricci tensor, Ricci curvature is positive, then this equation has a solution. So the result that I'll be talking about, which is trying to work with TIm Buttsworth, that kind of kicks from this theorem. So I will describe the setup of this theorem as well as Hamilton's proof in some detail. That would provide some more motivation for the work that we do. Okay, so what is this manifold? We're looking at the three sphere with the action of SO3 times Z2. Let's first ignore the Z2 part and just look at the action of SO3 on the three sphere. This is the one dimension up version of the usual rotation action on the two sphere. So there the orbits are the circles of latitude. Here the generic orbits of this group action are two spheres collapsing at the endpoints to these fixed points of the group action. Okay, so that's the basic SO3 acting on three sphere. And we also have this additional Z2 symmetry, which is reflection about this middle S2 orbit. Okay, so that is the setup. So let me talk a bit about the proof of Hamilton's theorem, which is essentially an existence result. So you have an invariant metric T on this manifold, which we write in this form as a sort of work product metric. T1 is the tells you the square of the radius of each S2 principal orbit, and we're seeking a metric G of the same form. Okay, so since the tensor T is given to us, we can assume that we've parameterized by arc length over there. So that's why we just have the dt square here, and we are seeking a metric G. So that's why we have this extra parameterization factor here, because we can't necessarily assume that the orbit space there is parameterized by arc length. So in this cohomogeneity one setting, the metric, since it is described by a function of just so don't really bother about it, just note that it is. And like so
I'm sorry.
many
I'm sorry.
existence questions for various,
Can
yeah.
you hear me, Anusha? Yeah.
Yes, I can hear you.
Can you repeat the last part of the ODE? Because we have a problems with the internet, so I couldn't hear. Can you repeat, please?
Oh, okay. Sure, sure. So I just said that this thing in the box is the prescribed Ricci curvature equation in this setting. Since we have everything is a function of just one variable, it's a cohomogeneity one manifold. So the prescribed Ricci curvature PDE becomes the following ODE system in these two functions. Yeah. Yeah, and you don't need to bother about the exact form, just notice that it is an ODE system. And like so many existence questions for geometric PDEs in the cohomogeneity one setting, the tricky part, maybe you can get local existence, but the tricky part is closing up your solution to on the singular orbits to have a smooth metric on the whole manifold. Okay, so here I should mention that in order for the metric G to close up smoothly on this closed manifold S3, its components need to satisfy some conditions at the two endpoints. For example, since the function f is the radius of this two-sphere principal orbit, then as t goes to the endpoints 0 and 1, f had better vanish. Okay, which is this condition here. And right? It vanishes, and it also vanishes with specified derivative. Similarly, since I'm asking for reflection symmetry about this middle orbit, the functions there are at t equals 1/2, those functions are even. Okay, so the existence question now is an existence question for an ODE system satisfying these boundary conditions. So actually, for the metric to be a smooth metric, there are infinitely many boundary conditions. And this is something actually that Hamilton didn't address in his original proof. And if time permits, maybe I will talk about how we address that in our work. Okay. So, right. So now this existence question for this ODE system and two functions. Hamilton's idea it's a very neat idea, but perhaps somewhat ad hoc, to introduce this new function L, which is negative f prime on H, and look at the ODE satisfied by that. Okay, so we seek a function L satisfying the following ODE with the following boundary conditions translated from the boundary conditions satisfied by F and H. Now, since the okay, and inherent is that once you solve this ODE, it is possible to recover back the original functions F and H. Okay, right. So the very first step was to convert the ODE into a simpler one, and notice that if you look at this ODE, you see that the growth in L is essentially linear. And so if you look at this as a shooting problem, start off the ODE at t equals 1/2, and let's see how long you can solve. Can you solve all the way up to t equals 1? And is it going to end up with the right boundary condition at t equals 1? Right. So solution to 1 and 2, which means start with the initial condition L of 1/2 is 0 and solve this ODE, that solution exists certainly if C is large enough. Okay, so notice that the only possible thing that goes wrong here is if you have something negative, in the square root, but by the conditions on T1, since T1 itself corresponds to a metric, and if we assume C is large enough, we can guarantee that the stuff in the square root is non-negative. Okay, so you can start off the solution from T equals 1/2 all the way up to T equals 1, provided C is large enough. Then the idea is to keep decreasing the number C, which now is a parameter for the solution, and keep decreasing it until the first obstruction to existence, and see what happens there. So it turns out, right, so the first obstruction to existence would come from the stuff under the square root becoming negative or becoming 0 at some point T naught, which also implies the following condition on T1 prime at that point. Now, in addition, if we have some assumption of monotonicity on the function T1, namely that T1 prime is negative on this open interval, then we can conclude that in fact, this first point of obstruction to existence must actually have been the end point of the interval. And the proof is then complete with showing that this condition that naturally occurs at the first obstruction to existence, that does imply the remaining boundary condition. Okay, so again, his idea is to start off the solution. If the parameter C is large enough, you can start off the solution and keep decreasing C till you reach the first obstruction to existence. And there, the monotonicity conditions help you to show that obstruction to existence must have happened at the end point of the interval. And then finally using smoothness conditions for T, which is itself a smooth metric that gets you back the final other boundary condition. And that's a sketch of Hamilton's theorem. And I wanted to present it because the functions here are less complicated than what we'll be talking about. And so this gives a good idea of the, the general strategy or the plan for the proof. Right. Couple of remarks that in the original statement of his theorem, he asks that the tensor T or the metric T that we are trying to prescribe as Ricci tensor, that itself should have positive Ricci curvature. And this condition is equivalent to T1 being concave, which in turn guarantees monotonicity of T1, which gets used in this step of the proof. Further, Hamilton shows also that you can have non-existence if T is not assumed monotone. So yeah, he gives an example of non-existence there. So it's certainly necessary to have some kind of condition on T. Right. So this was this result of Hamilton from the 80s. And since then, there's not really been any other existence results for prescribed Ricci curvature on cohomogeneity 1 manifolds. The next logical step maybe seems to be to look at maybe spheres of higher dimensions. And so sphere of higher dimensions with a rotationally symmetric metric, the proof would work out very similar to this one. What we look at instead, as one step further, is prescribing Ricci on a product of spheres. So in terms of the cohomogeneity 1 manifold, this goes from an isotropy irreducible principal orbit, or representation of the principal orbit, to one having two summits. Okay, so this is the action. SO3 times SO3 times Z2 acting on this product S3 times S2. So what is this action? It is a product of the original action that we had on the in Hamilton's theorem, just product with the following the transitive action of SO3 on S2. Okay, so in this case, the principal orbits of this group action are S2 times S2, which collapse at the ends of the orbit space to S2s. Okay, so the singular orbits are S2. And then we also throw in the extra Z2 isometry, which is reflection about the midpoint of the orbit space. Right, so once again here, similar setup, we have an invariant tensor T, which is itself assumed to be a metric. We parameterize it by arc length. And we seek an invariant metric satisfying the prescribed Ricci curvature equation with scaling, which is the following ODE system. Again, the exact form is not important. So all the smoothness conditions or the boundary conditions that we had for H and F1, they follow through. We just have this additional boundary conditions for F2. Okay. F2 being the radius of the second blue sphere factor. Right. So on the face of it, this is just like adding one more function to the same kind of equation. What's really different? Well, if you look at the equation for the S2 factor specifically, let's just focus on that for a minute. So it's this following second order ODE with Neumann boundary conditions. Then in the very special case that the tensor T is such that T2 itself is assumed constant, then it turns out you can explicitly solve the system and show that, or using the Neumann boundary conditions, you can essentially, by a maximum principle type of argument, show that F2 must be constant as well. And then the constant number C is determined uniquely by the following expression. Okay, so in this very special situation where T2 is assumed constant, the factor C, the scaling factor C, is already determined uniquely, which means if we look back now to the equation for F1, so the other two equations, the equation for H and F1, those essentially are Hamilton's original equations. However, we already determined C. Okay, so we lost that degree of freedom there. So this suggests that we need another constant. So in this prescribing Ricci curvature on this product manifold, it looks like we need another constant. So the problem that we actually consider now is this problem with two scaling constants. Okay, so scaling constant C1 on this part corresponding to the red S3 factor, and C2 on the metric on the S2 factor. So we seek an invariant metric G as well as positive constants C1 and C2 that solve this equation. Okay. Right. So my discussion on the previous slide perhaps provides some motivation or some justification for having the two different scaling constants. Um, Another case you could think of is if you're looking at actually a product metric. For example, if you think of the two sphere factors have different dimensions and so different Einstein constants. So perhaps that also gives some motivation why we should require two scaling constants. And the discussion on the previous slide suggests that even in the case where what we're looking at is not metrically a product, it's this kind of what product metric, but still it suggests the need for two scaling constants. Right. And more generally, we consider the similar actions of products of orthogonal groups on products of spheres in higher dimensions. So again, have an invariant metric T and ask to prescribe that as the Ricci tensor of some invariant G. Right, so ready to state the main result. Um, so our main result is that we prove existence for the prescribed Ricci curvature with two scaling constants problem mentioned on the previous slide. Okay, right. So that's basically what this theorem says, that we prove existence for this modified problem with these under certain monotonicity conditions, and so I'll mention below what those are. Right. So some remarks about the result, apart from right. So one remark is that to our knowledge, this is the first existence result on cohomogeneity one, closed cohomogeneity one manifolds after this work of Hamilton in the 80s. And our method of proof involves freely specifying these two quantities, so A and B. So what are these? The first quantity A is the radius of the first sphere factor in the middle. The quantity B is not very intuitive. Could think of it as some kind of energy, for want of better word, involving the second function F2. Um, right, it would have been nice to specify independently the function F2 as well in the middle, but right now this is the best we can do. We use right. So we obtain this kind of two parameter family of solutions, freely specifying these two quantities for every such choice of positive numbers A and B. We have a solution consisting of C1, C2, and invariant metric G. Okay. Right. Just mentioning the monotonicity conditions mentioned above, they Here they are, some monotonicity conditions on the functions Ti. These are guaranteed if the metric T satisfies the following conditions on its sectional curvature. Um, all right, you could think of these as some analog of Hamilton's assumption of positive Ricci curvature for the tensor T. Okay. Another comment is that this theorem also applies to a product of sphere with G mod K, where G mod K is an isotropy irreducible space. We just mention it for the case of the product of spheres because that just for simplicity. Okay, I guess I'm out of time. So I just say that the proof generally follows the outline of Hamilton's proof, but just having more functions in this case complicates matters very significantly. The analysis gets a lot more messy. But the basic idea of the proof that is showing existence, satisfying some of the boundary conditions for a large enough parameter C, and then having a sequence of solutions that converges to a solution that also satisfies the right boundary condition at the other end. That's the basic idea. Finally, we also do some bootstrapping to show that the metric closes up as a smooth metric at the other end, using something essentially related to results of de Turk and Castan. Right. Okay, so that's all I'd like to say for now. Thank you very much for your attention.
Thank you, Anusha, for the nice talk. Is there any question for Anusha?
Yes, may I?
Yes, of course.
So, can you say something about uniqueness of the solution from your approach?
Well, no, right now we can't all we can say is that we can freely specify these two quantities. So we have a 2-parameter family of solutions in that sense. But that would be a very interesting question for further study, including also what do really these constants C1 and C2 what do they signify geometrically? Yeah, but right now we do not know.
Okay, and under these monotonicity conditions, the original problem with C1 equal to C2, do you have non-existence results? I mean, can you show a T without any solution?
Yes, I believe the example given by Hamilton should work here, because the metric on I think essentially this example that I talked about, if T2 is a constant, okay, so if T2 is a constant, that forces F2 to be constant, and then also the constant C2 is determined. Okay, so then after that we can have since the other problem becomes a problem reduces ultimately to Hamilton's equations, we can show non-existence there by choosing an appropriate
So Hamilton
profile
example
of T1.
satisfies the monotonicity conditions, the T1.
No, sorry, I missed that. Let me think. Yes. No, I'm sorry. I should understand your question again. Do you ask if I allow two constants, then does the existence fail without these monotonicity conditions? Is that your question?
Yeah, assume the conditions, but a solution for C1 equal to C2, so like the original problem.
Yeah.
You can do a T like Hamilton without any solution.
No. I was mistaken there. Sorry. Hamilton's example would not satisfy this monotonicity, so that is not correct. No, so I do not know how to prove that for this monotonicity also we require C1 and C2. Yeah, I cannot prove that as of now. Yeah.
Okay, thanks. Very nice talk.
Is there any other question or comment?
Can I ask a quick question? Anusha, these two parameters that you can freely specify, A and B, A, I guess it's easier to see what it is, right? Is that the maximum also of F1 or?
Yes, it turns out that the solution also, the Fi's also have this monotonicity property. Yeah. So yeah, the monotonicity is like T1 is concave. So F1 also turns out to be so.
Okay, and then B, what, like, I was just trying to think geometrically, what do A and B mean? So A somehow is the size of that direction, right? Is the largest magnitude for that Killing field. What is B geometrically? Is there, or it's just something that cooks up from the equation, or is there a geometric way to see what it is?
Yeah, unfortunately, I do not know any geometric interpretation for that. It is just something that helps in making estimates for the ODE for existence for the ODE solutions. Yeah.
All right, thanks.
Yeah, it would be really nice to independently specify the radii of both the spheres in the middle. That could also give a way of extending this result to more manifolds, because the way we prove this is essentially on one half of the manifold. And since we're looking for reflection symmetric, you can then glue them both together to get metric on the whole. If we could freely specify both F1 and F2 in the middle, that would provide a way of going to homogeneity one manifolds with two different singular orbits, for example. Yeah, but right now that's
I see.
Yeah.
Yeah, one other thought would be that if you degenerate the metric somehow, right? If you can freely specify it, you can send A to 0 or infinity or something. That might give you further non-uniqueness with bifurcation. So if you look at the Morse index of these solutions, if they explode as A goes to 0 or infinity, then you might get even more solutions, I guess, addressing Jorge's question about of uniqueness. But
I see.
That's something maybe that shouldn't be too hard.
Thanks. Yeah, that's very interesting. Yeah. Thanks for that.
Is there any other question or comment? Well, if not, we can thank again Anusha. Thank you very much.
Thanks very much.